This video is an example problem for Professor Mokadam's construction layout and site development course. In this problem, we're going to be trying to find the bearing of two lines. Those lines are A1, shown here with a length of 210 feet, and line A2, which we do not know the length of. The other information that we have is that at point 1, its angle is 50 degrees. We know that the length of the line between point 1 and point 2 is 260 feet, and we know the bearing of that line is north 49 degrees, 40 minutes east. Given this information, finding the bearing of line A1 is going to be fairly simple for us. Because we know the bearing of this line and we know this angle, we can add these in to get an azimuth. So we take our 49. Actually, the way I'm going to do this to make it easier is instead of converting to decimal, because it's going to kind of be unnecessary here, what we'll just do is take this 49, add 50, till we get 99, and then we'll still have these 40 minutes left. So this is 99 degrees, 40 minutes. We cannot express that as bearing because it's greater than 90 degrees. So this is an azimuth. But fortunately, we can easily convert azimuth into bearing. We know that because we've broken down past 9 degrees, this is going to be a southeast line. Well, I say southeast because we actually want A1. So it's actually going to be a northwest line. But that's okay. We can still work with that because of some of the great properties of bearing. So all we have to do now is, if we just say there's an imaginary east-west line here. Actually, we can go ahead and draw this out. We'll say there's an east-west line here. This is approximate, not necessarily exact. And we'll say that there's a north-south line about here. I may not have those exactly perpendicular, but I think it illustrates the point well enough. So we know that we're down here. All we have to do is subtract this 90-degree segment here between these two imaginary lines. And we'll find that, pretty simple, that this angle here, between this little sliver of triangle and the line A1 over here at point 1, is going to be 9 degrees, 40 minutes, because we've taken the 90 away. Well, that's not exactly what we need, because bearing does not come from this east-west line. It comes from a north-south line. But we also know that right here between our imaginary lines is another 90 degrees. And so all we have to do then is subtract that 9 degrees, 40 minutes from 90. We also could have done this by subtracting this from 180. Either way works. Let's go ahead and do it through 180. So we'll go ahead, and I'm just going to do this mental math. It's going to be, we're just shy of 100. You're going to have 80 degrees, and then the remainder to get to that extra full degree to make it 180 is going to be 20 minutes. So this angle here is going to be 80 degrees, 20 minutes. And we can check our math on that if we want to. Of course, 40 plus 20 is going to be 60, which gives us a full degree. We can add that degree over here to the 99 to get 100, add the 80. It's 180. So just make sure that you don't forget about those minutes whenever you're doing these flip-flops. That can catch you up. You can end up adding a degree or losing a degree if you're not careful. So just pay attention and make sure that what you're doing makes sense and adds up to the 180, to the 90, whatever it is you're doing. Make sure that it adds up when you're done, that it makes sense. So having that information, we know that angle right here. And since bearing can, how do you say this? Well, let's actually just show it, because that'll be easier than trying to explain it in words. If we have an imaginary line here, that also runs north-south, we can use the opposite interior angles theorem, I guess is what they call that, to say that this line, A1, goes between them. So between this imaginary line and that is also going to be 80 degrees, 20 minutes. And so that means the line A1, it's pointing in a northwest direction. So it is north 80 degrees, 20 minutes west. Whereas the line 1A, so the opposite direction, would be, south 80 degrees, 20 minutes east. But that's not what we're looking for. We're looking for A1 in this example. So very important to pay attention to that, because otherwise you'll get them flip-flopped. So now we have that. We could do the same thing we just did to find A2, but we don't know this angle. Fortunately, we have enough information here to where we can use law of cosines to solve this length here, and then we can use law of sines to find this angle and work from that. So we will do, I'm just gonna write it out, then we'll put it in the calculator. We'll do 210 squared plus 260 squared minus 210, 260 cosine 50 degrees equals, and that's going to be the line A2 squared. Kind of a funny way of writing that maybe, but that's what we're going to deal with. So 210 squared plus 260 squared minus 210, 260 cosine 50. Take the square root of that, and we end up with 203.734 feet as the length of line A2. We don't need to know the length though, we need to know the bearing. So let's go ahead, use law of sines to find out what this angle is so that we can find the bearing. Go ahead and take sine 50 divided by that 203.734. We'll multiply by the line length opposite of point A. So multiply by 260, and then we'll take the inverse sine of that. We come up with 77.8 851 degrees. I'm going to say 3 decimal places is probably sufficient here because we're not even getting into seconds in resolution with the given information. So having 77.851 degrees, we can go ahead and just come back in towards north from this existing north 80 degrees, 20 minutes west. Now, let's go ahead and convert that to decimal real quick. I can tell you just looking at it, that's going to be north 80.333. I mean, it's going to be 333 repeating because 20 is 1/3 of 60. So degrees west. Well, we'll subtract that 77.851. So let's go ahead, in order to just get an exact number, I'll do that 20 divided by 60. I'll add the 80 back to it. And now let's go ahead and subtract that 77.851. And we get the remaining angle over here of 2.482 degrees. That's just that little sliver here between A2 and our north-south line that's going to represent that deflection from north to the west that is going to be our bearing. So let's go ahead, convert that over to degrees and minutes. So we are north 2 degrees. We'll take this 0.482, we'll multiply by 60, oops, miskeyed, multiply by 60 to get 28 minutes. We have 0.92 remaining, multiply that by 60 to get seconds, and we get 55.2 seconds to the west. We could take this further and solve line length here if we wanted to, but that isn't asked for. It just wants to know the bearing of those two lines. So the bearing of A1 is north 80 degrees, 20 minutes west. The bearing of line A2 is north 2 degrees, 28 minutes, 55.2 seconds west. It's debatable whether this high of a degree of resolution is necessary based on the given information not going into seconds, but I don't think it hurts to add a little bit more precision just in case that's called for. But that's all there is to that. Pretty straightforward.